All right. Hey, I'm David Hulton, or Hikari. This is Johnny Cash, and also Beetle is going to be doing a quick thing. He just figured out something last night, so I thought he'd come up here and present something real quick. So yeah, this is our contact info here. I help run TourCon down in San Diego, and I am part of like this Open Ciphers project, where basically we're trying to get cool stuff running on FPGAs. So mostly related to crypto stuff, but anything cool. And here, Johnny Cash, why don't you introduce yourself?
Okay, I'm Johnny Cash. I currently hack on wireless stuff pretty extensively. I'm going to talk about most of my code a little bit later. And I go to the Naval Postgraduate School. And also, I'll be graduating in September and looking for a job, so hire me.
I guess Beetle can introduce himself later when he does a little thing.
Yeah,
he doesn't need any introduction or anything.
Whatever, man.
So, first thing, I'm going to go over cow patty. Has anybody here heard of cow patty at all? Yeah? A couple people? Anybody heard of air crack? Yeah? Okay, cool. So, yeah, if you don't know what cow patty is, it's basically a WPA cracker. I just stole a bunch of slides from the presentation that the Church of Wi-Fi people gave, and I kind of signed up on the Church of Wi-Fi site like a few days ago, and so I'm not like officially a part of it, but it's kind of pending, I guess. They weren't opposed to me stealing their slides, so. Then Johnny's going to talk about Airbase, which is this web cracking kind of framework that he built.
He means 802.11 suite, by the way. It does everything.
802.11 suite.
Yeah, it's a suite.
And then we'll just talk about like how everything ties together. So first I'm going to steal some slides here. Wow, that works too. Cool. Wow, that's twitching a lot.
It's intentional.
Yeah, so here's some like introduction stuff. I haven't really read over these slides at all, so this is kind of a history of the Church of Wi-Fi. If you think that you want to work on some cool Wi-Fi stuff, just check out their website and sign up. And they got a bunch of different projects going. This is just one of the many that they presented on at ShmooCon. So they called this project basically modifications to cow patty, the J Dumbass project, or Dumas if you're French or something like that. And basically, cow patty, normally you'd kind of like capture some data and then run it through like a huge word list and see which word list matches, the data that you collected. And they just wanted to make it so they could pre-compute all this stuff and look for like really easy and dumb passwords that people usually choose. And so you can just pre-compute everything ahead of time and then, like scan through the list really quickly and brute force everything like while you're driving through a city and stuff. So basically, as access points come up, you just look through a file. If it matches, then you've cracked the network and you can just move on. So yeah, they really just tried to speed everything up and catch the low-hanging fruit with this. So yeah, they call it the J Dumbass project because as an user, J Dumbass, and yeah, a dumbass has his username as his password. So yeah, just basic passwords they wanted to easily check for. So I'm going to cover this a little more in detail, so I'm just going to skip over this right now. Essentially, they wanted to make it as a standalone application, and they ended up just modifying cow patty. They got Josh Wright to do all the modifications. And so they built this new program, GenPMK. Has anybody messed around with that at all? No? Yeah, Beetle? Okay. Yeah. So it's basically cow patty, but it creates a hash file, and then you can use cow patty to look up in the hash file instead of actually computing everything. So they basically took the top default SSIDs and ran it through GenPMK, because essentially with when you're computing your PMK, the SSID is kind of like the salt. And so you can't just compute a hash table and use it for any SSID. It's for a particular SSID that you compute it for. So they took the top 1,000 SSIDs and used a Perl script to basically like run GenPMK on all these 1,000 SSIDs for a given word list. And it essentially makes kind of like rainbow tables for WPA, but it's dependent on the SSID. So this is what they did at ShmooCon, and I'm going to talk a little bit how we expanded this whole thing. So yeah. So yeah, I'll just go on to the meat of the stuff. So essentially how WPA works is you basically have your master key, which is like your passphrase, and that gets hashed and turned into a pairwise master key, which actually is used with like your whole actual connection, like sending packets and authentication and all that sort of stuff. And basically what's used to transform the master key into the pairwise master key is this PBKDF2 function, which is actually an RSA standard. And essentially what PBKDF2 is SHA-1 HMAC that's run like essentially about 32,000 times total. Well, SHA-1's run about 32,000 times. SHA-1 HMAC is ran about like 8,000 times. And so this is the basic algorithm. You basically SHA-1 HMAC, like your master key, which is your passphrase, and your SSID, and just like a little counter identifier, which is 1 up here. And then you take that output and loop it back into SHA-1 HMAC as an input, and do that 4,000 times. And then whatever you get out of SHA-1 HMAC, that's like the first 20 bytes of your hash. And then you do it with a counter of 1 and do it another 4,000 times. And so this is really time-consuming. It takes forever on a PC. And I'll get into the performance stuff, but it's extremely slow if you're trying to go through tons of passphrases. So when you look at SHA-1, I looked in depth into SHA-1 because I was implementing this on an FPGA, and I wanted to optimize some of the stuff. So essentially, like a SHA-1 HMAC is you take your data and you XOR it with like a constant, which is 5C, and you have an inner SHA-1 where you XOR your master key with a constant over here. And then basically the whole output of this whole function ends up being the T value over here. So one thing that's kind of cool with this is that inside the SHA-1 functions, the master key is never changing, and you're XORing it with a constant value. So this value right here can be cached, and so you don't have to compute that SHA-1 every time. So you basically start out with that value, and just like it saves you, let's see, you have a total of like 4 SHA-1s here, so it cuts the amount in half, and so you can do some cool optimizations like that. So yeah, then essentially, once you have that, then you just analyze the network traffic, and then try a certain master key, a certain passphrase, and then if it matches up, then you know that you have the right key. So it's kind of like basic sort of password cracking. You just brute force everything. So I ended up building this stuff on an FPGA that uses 8 SHA-1 cores, and it uses block RAM to buffer all the different passphrases that are going into the SHA-1 cores. And then it's basically set up kind of like a FIFO, where as long as the machine is able to fill the buffer, then you can get full utilization on all the cores. And when you start like running slow on filling it, then it just drops down the performance a little bit. And I'll go into how that works a little bit. So essentially, you have your computer and your huge buffer where you're storing all the different passphrases that you're going to try. And so you fill in like the slot 0 here, slot 1, 2, and you fill it all the way down to like the bottom of the buffer, which in this case is 255. And so now your whole buffer is filled with different passphrases you want to feed into the SHA-1 cores. And then you basically have some FPGA code that takes out of those buffers, feeds them over to the SHA-1 cores, and then the computer over here is just kind of waiting for this whole block to finish. Once that block finishes and it moves on to the next block here, then it starts filling up here. So essentially, like if you start running slow on filling up the table, then it can still go through all these values down to 255 and still like fully utilize all the cores, and you don't end up with any sort of like performance loss and stuff. So I don't know, this is a really simple sort of kind of like a FIFO thing that I threw together, and it works pretty well for this. So you end up kind of developing custom sort of buffering schemes to like get extra performance out of things when you're dealing with hardware. So this is one thing that I threw together. So here's some of the performance results. With CowPatty on a Pentium 3, I was getting about 25 per second. So you could actually only try 25 per second. On 3.6 gigahertz P4, like my laptop, I was getting about 60 per second. A friend of mine tried on like the highest end AMD system that he had, and he got about 70. Beetle tried it on his Intel Core Duo and on his MacBook, and he got about 70 with Cow Patty. Supposedly, you can get like 100, 100 plus. Has anybody done any performance like stuff with AirCrack on a PC? No? Nobody's tried that? Okay. Well, supposedly it's a bit faster because they use MMX. So on the FPGA, on one of our low-end cards, which is basically just this little compact flash-sized card, I was getting about 430 per second. And in this cluster, this machine right here, I can do about 6,500 per second. And on our higher-end cards that are about the size of a PCMCIA card, I can get about 1,000 per second per card, so maybe about 15,000 for a system like that. And OK, so RenderMan already computed he did like the top 1,000 passphrases for the top 1,000 SSIDs. And his next goal was to do the top 1,000,000 passphrases for the top 1,000 SSIDs. And so he started computing this on his cluster, and it took him about a month to go through this whole thing. And then he found out that he had return characters at the end of every line. And so unless you have return characters in your SSID, he was kind of screwed. So yeah, after computing for a month. So he sent me an email, and he sounded kind of pathetic. He was like, oh, can you help me out, please? And so I coded this thing up. I finally got it working, and I actually started this cracking, the same sort of job earlier this week, like on Tuesday. And I finished it before I left for coming to the conference, and it basically took 2 days, like 48 hours. And actually, I have DVDs. It's 40 gigs worth of stuff. And I have DVDs here that we're going to give out at the end of the talk. I've got 4 sets here, so good questions, we'll get DVDs later. And thanks a lot to the guy over there selling the DVDs. What's that? He let me use the burner last night, so it saved a lot of time. So I'm going to do a demonstration. It's basically Cow Patty running on FPGAs with some Perl scripts involved. So I'll just run through this real quick. Let's see here. Aha. So I'm using RenderMan's account for this. Yeah, he basically just hooked together some Perl scripts run. Yeah. This is just his Perl script that he's using for computing the tables, and it's really simple. It just like reads in a file of SSIDs and then just spits off gen PMK for everything. So it's a total hack for just computing stuff. And building all these tables. So first, I'll show you how fast this runs on the PC here. I've got like a full dictionary file, which is let's see, 10,000 lines. I think there's only like 4,000 that actually are more than 8 characters. Yeah. And if you actually look at it, I put the actual passphrase for this test is family movie night at the very bottom. So that's what I'm going to run on the FPGA, basically 4,000. I created one for this demo because it would take way too long doing it on the real computer here. Let's try a small one. So the small one is like less than 300, and so it should be pretty fast. So I just made these little scripts so I didn't screw up the demo here. So this basically just runs Cow Patty with the test dump file with the dictionary. Oh yeah, fast. Yeah. With the small dictionary, and the SSID is something clever. So it took 2 seconds, did about 44 passphrases per second, so that's not too bad. Now I'm going to run it on one of the FPGAs in this cluster here. And I just added the dash capital F option onto here. And so you can just do dash capital F in the index of the FPGA you want to talk to. And then it just offloads everything to that. So it's the exact same cowpatty syntax for everything. So right now it's going through all these passphrases.
This is one FPGA?
Yeah. Yeah, this is just one of them. So did 434 passphrases per second, and found family moving night as a pre-shared key. Went through 4,000 in 9.4 seconds. And if you looked at GenPMK, it's kind of the same syntax as cowpatty. So I'll just run that real quick. So yeah, you just run GenPMK with a hash file, dictionary, SSID. So this is for the same really small word list with only like 89 passphrases in it. And then you just run cowpatty with the -d option, and you specify the hash file that you generated, and it just goes through and uses the hash file instead of computing. So 62,000 per second you can look up in the hash file. So it's quite a bit faster once you actually compute everything. And let's see. So here's it on the FPGA for the big one. So it'll take the same amount of time as the cowpatty thing. So there's the hash file. Then FPGA cowpatty, and then it just looks it up, and it's pretty fast, right? So basically, like if you happen to get one of these DVDs, or you BitTorrent them, or download them off a website or something, all you have to do is, I've got this test file that RenderMan sent me, and like if I'm trying to crack a Linksys access point, he's got this capture file, linksys01.cap. So all I have to do is specify your hash file. I've got like a Linksys hash file in here. Each one of these is about 40 megs. And let's see, specify your capture file. And SSID, which is Linksys, of course. I think it's towards the end. I hope so. There we are. Yeah. So yeah, that's basically it. If you happen to get one of these DVDs here, try it out and see if you can crack some cool stuff with it. Yeah. Yeah, we'll probably put them up on a website where you can just download the Linksys one. And so yeah, once you stumble on something, you can just download the file for that particular one. Or if you want, you can email me and I'll like compute like a few billion word lists or whatever for like that particular SSID. Yeah. Probably faster to compute them. So, yeah, last night Beetle tried looking around at some of the stuff with OS X for doing PMK stuff, and he found some cool stuff, so I just wanted to have him explain some of it. It seemed pretty cool.
Yeah, so real quick, you know how like there's IWconfig for Linux, and that's pretty cool, and OS X is pretty, and it's got nice little stuff for you to point and click. And I think it was like 2 years ago or so that I figured out how to write IWconfig for like Windows XP, because I couldn't stand like having to change SSIDs and actually like a GUI. So look for wireless weapons of mass destruction for Windows, and you'll find out how to write IWconfig for Windows XP. So I was thinking, well, I'll just do the same thing for OS X, right? And lo and behold, they've already done it. I'm like, yay! Because they were smart enough, right? They were working off a BSD subsystem, so I mean, it's great. This happens to hide in system library, private frameworks, Apple 802.11, .framework versions, current resources, and there's a command called airport. And you can do all sorts of command line stuff, just like IWconfig with the airport command. So if you type airport-h, you get like all sorts of crazy stuff. So you can do manual scanning. You can actually join a different network. You can change your preferences. You can look at the pre-share keys that you already have stored for your current networks, that sort of thing. But I was looking and I was like, oh, that's great. But then I saw, wait a second. There's just a regular flag that lets you just generate a pre-shared key or a PMK for a particular SSID, which is basically what GenPMK is for CalPatty. So as long as you just want to generate a whole bunch of PMKs for a particular SSID, you can do that with a shell script inside OS X by default. You don't have to download anything else. The performance is not great. So sure, go back. Yeah. System, library, private frameworks, then Apple 802.11 .framework /versions /current /resources, and then there's a command called airport that sits there. Yeah. And the first thing I did was create a symbolic link and use your SBIN, right? Because it's nicer to have it in the path, right? So performance-wise, here's like the shell, or it's a little bit of Perl that I wrote, and this is all it does. It just basically takes a dictionary file and then runs the airport command with those flags on that particular SSID, and then creates like your PMKs for you. Now the problem is that this format and what it's creating here isn't an actual hash table that's readable by CalPatty, but I wasn't about to figure that out right then. I didn't know exactly how he was storing like the header on his hash file to determine what the SSID was, so I was going to do that for later. So later on, it'll actually do this. Maybe I'll throw an update on like my website or something like that. Anyway, if you run it, you get about 10 and a half passphrases per second that you're actually generating, which is decent in comparison to like Pentium 2s or whatever. But what's nice is that you've got if you're doing this on a MacBook, then you really have two processors, so you can run it twice, and you actually get better utilization. You get 20 passwords per second. If you got a single core, you're sucking. Now, what's interesting is that I thought this was kind of cool, and I thought, well, I'll do this in comparison to GenPMK. So then I tried to compile GenPMK, and of course it doesn't compile cleanly on OS X, but I commented out a couple different includes, and then GenPMK does run on OS X. I haven't gotten CalPatty running on there, but what's nice is that you can actually get about 35, 36 per core, and so you end up doing about 70 passphrases per second with GenPMK. So Josh has still got the cool shit with GenPMK. Don't think that like this shell script replaces that in any way, shape, or form, but it's just kind of cool that you can actually just do this on the fly with a shell script.
Yeah. Cool, thanks a lot.
Does all this work for WPA and WPA2?
No, there isn't WPA2 support yet. I think that the only difference is that WPA2 uses AES instead of SHA-1. And so I think it'll actually end up being faster to do on FPGAs. But I haven't really looked at it much, so. Oh, go ahead. Oh, okay. Yeah, so it's just, I think that Josh Wright is going to be doing some sort of support for WPA2 into CalPatty. And if somebody else comes out with something before then I'll probably do FPGA support for it. Yeah, go ahead.
Can you talk a little bit about what the system is you have with, I guess, 15 or so FPGA cards and how that was put together?
Yeah, sure. This company that I helped start, we manufacture, let's see, I've got some cards in my bag over there.
Here's one.
Oh, okay. So this is actually a compact flash card like inside a PCMCIA adapter, and it's pretty small, but basically this thing plugs into a PCMCIA adapter, and then it plugs into a PCMCIA to PCI adapter, and this motherboard kind of backplane thing supports up to 20 PCI cards, and this actually has 2 motherboard blades in it. So there's 2 motherboards in here, and one can do like 8 PCI cards, and the other one can do 7, and so it's a total of 15.
PCI cards are actually the FPGAs that you're putting into that.
Yeah, they're these little tiny things inside, like, two adapters basically into PCI, into the motherboard. Yeah. So it's totally like off-the-shelf hardware that we just rigged together just to have a bunch of these in a single machine.
Where can somebody
These things we sell on our website at picocomputing.com. And I'll have a link for it later on in the presentation. But these are pretty expensive, so I don't know if your company's paying for it, then that's cool. If you're trying to do something by yourself, you can buy like pretty cheap eval boards from different places, and they're a lot more difficult to set up. You're going to spend a lot of time like building an interface to actually talk to them and stuff. But
Be a nice thing to put in your laptop with the appropriate.
oh yeah,
It is
yeah,
a
these
very
are really
nice thing.
convenient. I mean, you just pop them in and you can start doing dev work and stuff. So, but yeah, they're really expensive to manufacture. So that's mostly why they're really expensive.
So how much would your sound cost?
This box right here is like 50,000. Each card is about 2,500. So yeah, it's a little pricey. If you can go out and buy some dev boards, like if you just go onto Xilinx.com and search around for dev boards, they range between like maybe $300 and like $500 or $600 for like a kind of like bare bones Vertex 4. Spartan 3s run about like 100 to 200 if you want to play around with those. And the code that I'm going to have up on OpenCypher is you should be able to port it to pretty much anything. It's all, it's all pretty open. So go ahead. It's on Verilog on the FPGA. Yeah. Any other questions for this section? Yeah.
I know a little about hardware, but don't you create a bottleneck of some sort? Don't you lose throughput going through 2 adapters?
Yeah. There isn't really a whole lot of bandwidth going between the computer and the cards, because it's only doing like 400 per second per card, and that's maybe averaging like 50 bytes per like passphrase or something. So I mean, it's not that much bandwidth if you consider like how fast the PCI bus can go up to. But I was running into some limitations with 8 of them, where they were kind of like fighting over the bus, and so it wasn't running as fast as it could have been. So I was maybe getting about like 380 per second average across all 8. But with 7, it was working perfectly fine. Go ahead.
How many packets do you need in the capture file?
Packets? 6? 4? Yeah, I think it's the 4-way handshake that we had.
It's only 3. It's the last 3 of the 4-way people.
Somewhere in here. Yeah. Yeah, these 4. I think that, there's some sort of like 4-way handshake thing that goes on or something.
I don't think. Oh, wait. There you go. Maybe.
Yeah.
Sort of.
Kind of.
Yeah, not so much a point. There's 4
whatever.
things there.
So I think you just have to capture that thing or something. I don't know. I just crack the codes. I didn't really mess around with the other stuff. Yeah. So Johnny's going to talk about Airbase now. If there are any other questions. Oh, okay.
I have a question. So you're testing each one of these cards with like a SHA-1 HVAC over and over and over again, right?
Yeah.
Have you done any sort of estimate, or like based on like the average computer, like how many computers it would take to do the equivalent of say 15 of those cards?
Yeah. Well, okay. So like say cow patty does like 70 per second or something like that. Then like one of these does 43 or 430 times 15, so 6,500 divided by, basically about 100 laptops. Yeah, 100 dual core Intels, something like that. Yeah. So if you can buy 100 laptops for $50,000, then it's This probably draws a lot less current than 100 laptops, though.
And it's green.
Yeah, and it's green. It's green.
That costs extra.
Yeah, we even sell it with like some bling bling lights and a spoiler on the back too. Any other questions? Some decals. Anybody else? All right. Okay. Go for it, Johnny.
All right. So I'm going to talk about Airbase for a little bit, because the other thing we've implemented is hardware-accelerated RC4 inside a web brute forcer. It isn't quite as sexy as brute forcing WPA, but still, get your bases covered. And so talk about Airbase. Airbase is actually a lot more than just an 802 or a web password cracker. And since I'm talking about it, I'm going to go over some of the other features very briefly, because I wrote them and I'd like people to start using it.
You need to go click on the thing.
Hyperlinks and PowerPoints. This is amazing. Didn't know you could do this. Okay, Airbase. Airbase has pretty much three large components to it. It's got Airware, which is a library written in C++, and it's got JC WebCrack, JC AirCrack, and a bunch of tools. JC AirCrack is my re-implementation of AirCrack. It's written in C++, and it's way easier to read than Christoph's AirCrack. It has less features. I'm not going to say it's particularly faster yet, but it's definitely easier to experiment with, and I'll show off some other things it does. Then JC WebCrack is the thing we've actually gone and hardware accelerated so far. That's just a plain old WebKey brute forcer, distributed, looking kind of like City at Home cracking web keys. And Tools has a bunch of other utilities I'm going to mention briefly because they're really handy if you're into developing wireless tools. Assuming my spacebar works. What button does this take? None of them.
Is it frozen? The thing is
It is frozen. Okay, so hyperlinks in PowerPoint, a bad idea. All right, this takes two hands. Just a second. Shit. Oh.
The other any key.
Oh,
Who's
beach
doing
ball.
something?
Beach ball.
Yeah, beach ball. You can't see this, but Microsoft's Crash Reporter crashed. There you go.
Damn, she's sexy. Whoa! There's 100 of her.
Okay, so no hyperlinks in this version.
It worked fine with the other one.
It did. Oh, where is there? Okay. Much better. All right.
It's reversed.
It is reversed. I had this all working beforehand. Tools. One more time. I'm a brilliant computer scientist, I swear. I just can't work Microsoft products. All right. It does work. Okay. So, as I was saying, Airbase, there's three major components, AirCrack, WebCrack, and a bunch of tools. And they all use the same library, Airware, because this started as a bunch of legacy code. I had written so many different wireless utilities, and I was so tired of maintaining different code bases. I spent like 2 months and wrote what I think is a badass C++ library to do everything for me. So if there's any function that I ever had to write twice inside any of these things, they got crammed into Airware, for better or worse. So just to go over the tools that are included in this briefly, there's a PCAP to air file, so that does what you'd imagine, and take a PCAP and inject it. PCAP WebCrypt, which is a little program to decrypt and encrypt PCAPs with web. It's got some more useful features for developers. You can specify things on the command line, like I'd like to encrypt this packet n times with this probability of a weak IV, or set this IV to this, so it gives you a little more power than some. Airware test is a nice unit tester for Airware, and it does actually have some features. Prints out PCAPs, so it'll do some web benchmarking. Prism Strip is a little program that's poorly named that'll strip Prism headers, but actually it'll strip out AVS headers. And you wouldn't believe the number of crappy ways people will write down PCAP files. It's terrible. They'll set the data link type to this, but then they'll append a 4-byte frame checksum, which shouldn't be there, or maybe it should, but you can't tell. Handles all that for you. Actually, the library handles all that for you, so you don't have to think about it. Simple Replay is a little program that'll just replay packets on one interface, which is kind of nice. So it sits there, and you can tell it replay a data packet with this probability, or you can tweak it to do only whatever packets. And Craft Test is a little program in there that'll just run through the different crafters to show you how easy it is to craft various packets. None of these are directly really related to cracking web with hardware, except maybe PCAP WebCrypt came in kind of handy. So let's get to, the cracking utilities. First we have JC Aircrack, a reimplementation of, the ever-popular statistical attacks against Aircrack. Aircrack has 17 Corec attacks implemented. I only have 16 because one I could just not read or figure out. It's commented out and says XXX, don't put this in. So anyway, so there's a JC Aircrack binary. I have my own version of, I wrote my own arrow dump actually because I wanted to be able to run Aircrack in real time on a Mac. And the version that Christoph had, runs great on Linux but doesn't run on OS X in real time. So you can use this version of arrow dump to dump IVs or packet files in real time using the passive driver for your airport card if you get the latest Kismac and fiddle with it correctly, because it's not the easiest thing to do. But it does work. Getting the driver working is your problem, however. Other than that, pretty much re-implemented everything else. PCAP2 IVs, merge IVs, those do probably what you think they will. And these are all file compatible and buffer compatible even with Aircrack, so if you wanted to run my arrow dump on OS X and actually Christoph's Aircrack on OS X using, they'll talk to each other just fine. So that's JC Aircrack. And here's a screenshot in case something goes bad with my computer while I try to demo it. Hopefully, we won't need the screenshot. Just a second. All right. Okay. Okay, so here I am. This is the latest subversion release of Airbase, which isn't actually up on my webpage yet, but it will be shortly, I hope. I'm just not brave enough to put a subversion server facing the internet. So, got a little script here that's going to use pcap webcrypt to generate some pcap files to run Aircrack against. And, it's not as good as capturing packets in real time, but at least it's not that much tricks up my sleeve, right? So it's using pcap webcrypt to generate easier, pcap files that are easier and easier to crack with more packets and more weak IVs, so you can kind of see how the tool runs. And later you'll see how we're going to accelerate it in a second. So it's saves you time from actually trying to collect this data. You just generate it.
How well does this work with access points that filter weak IVs?
See, access points, there are plenty of access points that will filter weak IVs, which means they won't use them. But there's nothing that can stop an old client from using them. So you got some old Windows box laying around with a crappy driver, and it's still going to, use these weak IVs. And it's not that easy to filter them as people think. There's the classically weak ones that everybody knows about with FFs, but there's 17 different statistical attacks. It's not that easy to filter for all of them, and very few people do, I think. So if there is filtering, it's filtering the one attack that pays off the most. But all right, so let's give this a shot. Tell it the key size. Some debugging output is handy. Pass it a pcap file. So this is the hardest to crack pcap file that I generated, and it's probably not going to crack it or come anywhere near cracking it, but you can see how it works. So if anybody's used Aircrack before, they probably recognize what this looks like. It's a brute forcing a 13-byte key, and you can only see 11 bytes up on the display. The bottom two are getting brute forced in real time. So the time it takes this 9F to slide over is the time it takes to brute force 16 bits of the key at the bottom. So basically the way this whole program works is you read in all these pcaps or packets, compute some statistical functions over them, and generate weighted guesses on the value for the key. And all these weights are pretty even, and they're also pretty low. The key is 001122, and you don't see 01122 in here, so didn't do a very good job. There's just not enough data available. Let's try it with an easier file. Let's jump up a little bit. Okay, this looks a lot more promising. 001122. It's got a lot more of them. You can see the weights are higher up. The one handy thing for this is if you're actually trying to develop some sort of new attack, these the display down here is showing the number of the number of like that attack weak IVs it's found and the weight you've assigned to it. So the classical attack is attack 0. It's found 687 of those, and they get assigned a weight 5. This is different attacks, and this one's got weight 3. So that's useful for trying to see, if you're trying to gather some more intelligence on how these things work. Or I'd really like to see, for example, what happens if I'm only using the first attack. You can specify that. So if you're wondering, maybe I should weight this one higher. Let's see how it goes. All the other ones have their weight set to 0 and are displayed in red at the bottom, so you can see that. Well, if I don't have any of those other attacks, I didn't do nearly as well. I got 0, 0, no 1, 1, no 2, 2. Kind of fell out a little bit. It's kind of handy. You can also do the inverse, which is, again, useful if you're kind of interested in how this stuff works. So the way you hardware accelerate this thing is I've explained this to some people, and I wasn't going to go into it, but apparently a lot of people think the thing to accelerate is the computation of the statistics. And really, you only do that 17 functions over each packet you see once. So it's not that much computation time, really. The real problem is you're sitting there brute forcing the bottom of the key space. So you can change that, and let's say, now I'm going to brute force 1 byte at the bottom. And you'll see the display updates a lot faster, and there's only 1 byte you don't see. Similarly, I can 2 is the default, so if I jump up to 3, it pretty much looks like the program stopped. It actually isn't stopped, it's just brute forcing 3 bytes at the bottom. So you're going to sit here for a while. I haven't even waited it out, honestly, so it could be an hour or 2. What we'd like to do is get it so that you can brute force 3 bytes at the bottom with an FPGA. And this pays off better than you might think, because actually, the further you get from the top of the key, the harder it is to generate these statistics reliably. So it's actually better than, not only am I brute forcing 1 more byte just as fast, I'm brute forcing the 3 hardest bytes, which is, good. So that's aircrack. Let's get back to my presentation and hope this doesn't crash again. Any questions on that before I delve into other tools? I'm just kidding. You can ask me later, too. Okay. So, all right, I didn't need the screenshot. It all worked out. So JC WebCrack is the just plain old key brute forcer. There's no clever statistics. It's just study at home for cracking web keys. I actually wrote this, like 3 years ago, and I used it pretty effectively on a cluster. And so if you're curious, if you want to brute force an entire 40-bit key, you need about 24 hours with about 10 or 11 Athlon MP 1100s at your disposal. That's the worst case. So 12 hours on average, which is very handy. It's also the only way to know if you've got a 104-bit key, really. If you try all 40 bits of a lower one and it doesn't work, then okay, I got to start trying to do stuff to 104-bit. So JC WebCrack now has support for the Pico client, which is going to talk to the FPGA. So this is a picture of the JC WebCrack server, which is responsible for handing out chunks of the key space to clients. And I'll start it up later with FPGA, so I'm not going to get into it too much now. So this is the way it worked before. You just start up JC WebCrack D on some server somewhere, and you get a bunch of clients to talk to the server and check out key spaces. How you obtain these clients is up to you. The client would probably even compile and run on Sigmund, though I've never bothered. All this stuff runs on OS X and Linux and crosstalks for each other. So OS X server, Linux boxes, whatever. All plays nice. So you just got to get a bunch of client computers to do your work.
So when's there going to be the JC WebCrack worm?
No comment. So this is actually, I mean, people kind of think, why would you brute force a 40-bit key? And well, I'm like, because I have had a cluster. Now I have FPGAs. I had a cluster, so it was really nice for 24 hours. Worst case, turn your key around. So to accelerate it, now we just bring in the Pico client into the picture. So we've got our normal client sitting there talking to the server, checking out key spaces, and then we bring this one guy who's a little smarter, and he talks to the FPGA, and the FPGA does all the work for him. So you can intermix them as well. Currently, the way this works is that JC WebCrack D talks to the Pico client, and the Pico client talks straight to the FPGA. JC Aircrack, can I get my mouse over here? Yeah. JC Aircrack doesn't have any hardware support yet, which, you know, I'd like to get in there. But I was not going to hack it in too fast, like hack it into, you know, the client and then hack it into JC Aircrack. What I'm going to do is I'm going to do this, which is I'm going to try to throw all the hardware support I can inside Airware, so all of the programs suddenly crack stuff as fast as they can on that platform. If anybody's ever seen Core Image on OS X, that's pretty much the motivation for this. It's really slick. You give it a little program to do manipulations of graphics, and it'll either run it on the GPU or run it on the CPU in parallel as fast as it can. And the client code doesn't have to deal with it. Well, I'm trying to do the same thing here. I'm probably going to end up writing some other cracking tool at some point in the future, and I'd like to not have to rewrite all the code to talk to the FPGA. So what's going to happen in the near future, hopefully, is that Airware is going to have all this code that'll talk to hardware. Right now, we got FPGA code and, you know, software. There's other things you could try to do this on. GPUs are, you know, something people have toyed with, and there's compilers to target them. That cool physics engine thing, I don't know how the hell you talk to that, but that's another idea. And so then all the client code, you'd have a sort of simple JC WebCrack client. No longer does it keep track of the fastest way to do anything. It just calls Airware, and Airware figures it out. And as soon as I do that, JC Aircrack will immediately be optimized, which is nice. So that's going to happen shortly, I hope. So this is a little bit of details on how we actually talk to the card right now. Basically, the Pico client gets a key from the server, and it's like, okay, figure out what I'm supposed to do, and then it tells the FPGA where to start at, where to stop at, the size of the key, and the hopeful PRGA. The way this is implemented is that we know the first 6 bytes of the random output from RC4 because we know the snap header of every packet. So we can XOR out 6 bytes of every packet and get the output from RC4. So we're like, okay, then we just tell FPGA, do all these keys, and if you see one that outputs these 6 bytes, we've probably got the key. There could be collisions. I mean, it's only 6 bytes. It's pretty unlikely. So then the software actually has to kick in. Okay, hardware says it's this. The software is going to double check and make sure it works. And then, you know, it's like, okay, we got the key. So that's just everything I have in Airbase. So now we're going to try to do a demo, right? Hope for the best.
Oh, demo of the, oh, that stuff?
Yeah.
Oh, I got some slides.
Oh, sorry.
So I can go over that real quick.
Okay.
And I can do the demo.
Yeah, let's hope it doesn't crash again. Here.
Okay. You kind of already explained some of the FPGA stuff, but I've got some diagrams here that might illustrate a little better. Let's see. There we go. All right. Damn. Okay. So right now on the FPGA, we've got 16 RC4 cores that we built. It uses block RAM for S boxes. So basically, the main problem with running RC4 in hardware is that you've got this S box that, you know, works great in software because it's just RAM, but when you're dealing with like 256 8-bit registers, it takes up a lot of space. And so with block RAM, it's kind of like little tiny RAMs that are almost kind of like cache on your processor. So they're really fast to access, and so we just decided to use those for the S boxes. And yeah, it just tries every key between the start and the end. So if you've seen RC4 before, it's a really simple algorithm. You basically just have this initialization step where you set your S box to just like a permutation from like basically 0 through 255 inside this buffer. And then you kind of do a bunch of mixing in the KSA. And then for the PRGA, you do some more mixing and like pull out values here and there. So it's an extremely simple algorithm in software, and it's actually pretty simple in hardware, but you just have to pull some different tricks and stuff. Basically, for an RC4 module, you just look at your inputs and your outputs, and you try and tailor something around that where you get a certain input and, you know, it gives you the right output. So for this particular module, basically your key is your input, and your PRGA is going to be the output. And one of the problems here, and this is basically how it cracks it. You have like some sort of expected PRGA, and sends out like key 0, key 1, key 2, and then it gets back some sort of PRGA, and this is normally supposed to be like hex values, but just for like artistic value here, threw those in. And so it keeps on going along, and then, you know, finally, oh yeah, there's bling. Okay, yeah, I got some bling. You got some bling. Yeah, we're all good. And so then it says, okay, so that must be the key, and then it just reports it back. One issue with this is that you end up wasting lots of cycles just initializing this SBox value here. And so essentially there's like 256 cycles to initialize this. Then there's another 256, maybe 512 to do this whole step, and then an additional like 8 to 16 or something like that to do that step, just because there's so many iterations that are dependent on the previous ones. With this initialization step, you can actually do that kind of in parallel. And how we do this is we have our initial SBox that, you know, the computer writes the values to. And then we just have the SBox write it out to these different blockrams that are associated with these different RC4 cores. And then after those are filled, then the RC4 core uses that SBox, and it'll end up, you know, writing values into it, and it'll do all sorts of like mixing and stuff. And meanwhile, while it's doing that, we fill up these other block rams. And so we're actually doing the initialization step for the next RC4 run in like the previous one. And so then after it's done with this RC4 step, it moves on and uses this one, and, you know, pollutes that one, and then, you know, switches back and forth. And so that's kind of like one optimization that we came up with for doing this whole thing. So now here comes the demo. Basically, JC web crack plus FPGA plus the matrix.
Cross your fingers. Tell us if I insert the card the right way. Okay. So this is startup. So just starting up JC WebCrack D, the same old server we've had for quite a while. So got the pretty curses interface. If you haven't figured it out, I like curses. And I've also clearly had Turbo Pascal influence my interface design since I was a child. Just can't kick it. So it's you can see it's got a chunk size. You can tell it how many bits a client wants to check out, or how many are out, and how long to wait until you think that, oh, that chunk's not coming back. So let's start up a client. Cross our fingers. Oh, okay, good. It's reading the keys off the FPGA right now in real time, and it can redraw the screen this quickly because it. Yeah. Thank you. The real beauty of this is I've showed this to people and they're like, John, you're wasting CPU cycles drawing the screen. And then I'm like, no, I'm not. I'm doing everything on the card. There is no, you know, the CPU usage right now is like 0%. So you can sit here and draw whatever you want as quickly as often as you would like, and you end up with something as pretty as this. I think the key I started it at was 0004, so it'll get there in like, I don't know, a minute or so. Okay, let's see a top.
Oh, we got to see the finish though, right?
We'll make it.
Okay.
Oh, here we go.
Ah.
So CPU usage 0%.
Nice.
So you could just start up another, you know, JC WebCrack CPU bound one too and do twice as fast. But let's go watch this. Okay, so.
Cross the fingers.
Yeah, key starts with 0004. There is no spoon. Oh, the suspense. There we go.
Nice.
Thank you. You would not believe how many nights I spent sending raw terminal codes to get that thing to look right. Because I didn't use curses, because I'm just old school. That's the next release. Oh, there is one more thing. You can change the color as well for you Matrix purists. Got to start the server. So don't ask me how I did the Matrix thing, because I won't tell you, because I showed somebody this. I'm like, dude, that's awesome. I'm like, yeah. They're like, how do you do it? And I told them, and they're like, that's way less cool. So it's a secret.
Copper carded?
Oh, right. Okay. Can't change it on the fly yet. That's a future feature. There you go. So, any questions on anything, I guess? We're done with the rest of the presentation.
What's the meaning of life?
42, next.
Actually, I have a question for you on using webcraft. You know, did you actually build on what you built before?
You mean, is this using the previous code I wrote? Yeah. This is talking to the same server that I've been using for a couple of years now.
You're saying that you built webcraft?
Yeah, the first distributed webcraft version. Yeah, this is still even using the same protocol. So it's still the same server, still the same protocol. They interoperate. It's kind of neat. So, any other questions?
So, how much faster? It's been shown that you can do packet injection and crack wrap in like 11 minutes.
If you're really, really lucky, but yeah, packet injection helps.
So, does this accelerate that?
No, AirCrack hasn't been accelerated yet. Well, like I said, I got to get this code merged into Airware, and then everything will be accelerated. But yeah, it would help a lot.
Yeah,
Still,
you need less packets and stuff.
Yeah, still the thing is, there's a huge trade-off between like 100 more packets and like an hour more CPU time. You would really rather have 100 more weak packets than another, gigahertz, probably. So more data helps more than more CPU cycles. Anyone else? Hard to see with the lights.
All right.
Sure.
When are you going to give away the DVDs?
I guess at the end. Or we can try and figure out who asked questions earlier.
Yeah.
If we don't make the drawing for the DVDs, are they purchasable?
Yes, they are. How much you guys got?
Step 3.
Yeah, step 3, profit.
Profit, baby.
I don't know. I think he can burn 7 DVDs at a time and probably has a bunch of extra DVDs laying around.
Yeah.
So. Cool. Yeah, there's let's see, other important slides.
Huh? Oh, hey, slides.
Yeah, there's a couple other slides, but whatever.
Oh no, we got performance numbers. I'm sorry, I forgot.
Yeah.
We actually computed something.
Yeah, there's performance stuff. So yeah, that's the performance. Yeah, on one of these cards in here, we're getting about 2 million per second. We can probably increase that to like 3 or 4 if I optimize stuff some more. So yeah, it's a bit faster. So yeah, now we can like brute force 24 bits really fast instead of 2 bits or 16 bits or whatever, or 1. What's that? So conclusions: get an FPGA and start cracking. Make use of your hardware to break crypto. Add cool matrix ASCII effects when you can. Choose bad passwords, please.
Or 40-bit password. It can be anything you want then.
And so yeah, now we're going to do questions. I guess people that asked cool questions before, just ask them again, and we'll give you some stuff or something. But yeah, so any questions? Even though we've already probably gone through a bunch. Oh, yeah.
Okay, can you talk about the hardware?
Okay, why don't you come up and get some DVDs? I'm not going to answer it.
Well, you already did.
Yeah. Yeah. Did you asked a couple questions, right? Yeah.
Dave, how many gates are on the one of the FPGA?
One of them? Like one of the cores or one of the cards?
One of the cards.
One of the cards.
3.
Yeah. One of these LX25s is equivalent to supposedly like 1.5 million gates, roughly. So, yeah, they've kind of switched away from the whole gate concept to like LUTs or slices, and so they're using totally different metrics for everything. Yeah, you have to take all 3. Yeah, there's 9 DVDs total.
I looked in one and it had a label. Okay.
Yeah. So yeah, just take a stack of 3. Oh, okay. Yeah, it definitely would be. We're just, we're. Yeah, exactly. Like, we didn't have like tons of budget to have a bunch of different projects going on at the same time. So right now we've just got this compact flash one. We've got a card bus based one, and we're gonna have an express card one pretty soon. And pretty much all those you can adapt to like PCI or PCI Express or whatever. So that's good enough for now. We'll probably do a board like that later. But right now you can find lots of PCI boards out there. So.
Right. I was just wondering why you didn't go with more density in the PCI. You get 16 cards.
Oh yeah. I don't know. We're thinking about doing something like that, but there's other places out there that do stuff like that. So. Okay. Go ahead.
What kind of beer do you like?
I don't know.
That's a good question. That was my question.
Actually, I almost forgot I got some Guinness up here, so you get a beer. Anybody else have a good question? Beetle, you want a Guinness? Okay, here you go. You want to get one?
Chuck 'em.
Okay, Data?
What is an affordable FPGA? I can't spend $2.5 on one. Spartan 3.
Oh yeah, Spartan 3s are really cheap. You can just go onto Xilinx.com and search they have a directory of all their different dev boards. And you can get like a starter Spartan 3 with like, I don't know, 500,000 gates for like $100, or like one with like 1 million gates for, what's like a 1 million gate one would be about like half as fast as this. You could probably get maybe like a 2 or 3 million gate sort of range one which would be about equivalent to this, for maybe about $300 or $400, like in the Spartan 3s, and kind of the same for Vertex 4 if you got one of those.
If you're a student like in an engineering university, you can normally get them through like the electrical engineering. Well, I'll to call some people and get an ID made.
You want a beer? Or you want some tables? Oh, go ahead. No, there's an or there.
Yes. You have to know your priorities. Tables or beer.
Yeah, sure, why not? Okay.
Have you ever considered maybe a web crack at home distributed project?
Oh, kind of like say at home?
Yeah.
Yeah.
Why? You've got FPGA.
I don't know, maybe ask Beetle about it in 6 months or something, right?
No. That would just be crazy.
Beer? CD? Go ahead.
Do you guys sell like whole solutions like that? Like, do you sell that box, you know?
Yeah. We can. If you want one of these boxes and you give us $50,000, we'll give you a box. So.
Huh?
If you're.
I don't know how many.
Yeah. Any color.
Yeah.
Any blinkies.
You need 3.
If you're doing like some sort of. Yeah. There you
It
go.
doesn't work like that.
They're supposed to be 0, 3, and 6, right?
Yeah. Yeah. So. Yeah. What was the question again? Yeah. You can buy one of these from us right now. If you're going to do like some cool projects with it, we can give you a good discount on like the cards and stuff. So, just give me a call or send me an email or something. Any other questions, Eddie?
You guys talk a lot about you were defining your key size as being a start point and an end point.
Yeah.
Wouldn't that be more efficient if you just could specify the number of iterations you were going to take in the code rather than having to do a pair?
No, it's kind of the same thing. I mean, yeah, I guess it would probably be a little more efficient to compare like a smaller counter than like a huge value. But we're only really incrementing by like a maximum of 32 bits or something like that, and so I don't know. It's not too bad. Like on the FPGA, the difference between that is there's a lot of other stuff on there that's slower. So yeah. So I think you get a beer and Petty gets a beer. And any other questions? I think we're all out of beer, so I don't blame you if we. Yeah. Okay. All right. Thanks a lot, guys.